So all the lectures will be recorded and posted on the YouTube channel that is given on Blackboard. Let me start with some very preliminary information. The most important fact is that everything, syllabus, textbook, information about exams and homework, so all posted on Blackboard. So you need to check the Blackboard website for this course frequently. Also, homeworks and exams are all going to be done at home. And you convert your homework and exam papers to a PDF file and upload it to the assignment section of Blackboard. And that's the only way your work can be graded. So, and most printers, most people have access to a printer. Most printers these days allow you to scan a document and convert it to a PDF file. So normally when you do your homework or take an exam, when you're done, you'll put your pages in order, scan them to get a PDF file, and then you upload the one PDF file to the assignment section of Blackboard, and everything gets graded. There's a textbook for the course, which has a slightly obnoxious title of Linear Algebra Done Right. It's a decent book and it is relatively inexpensive, and those are the two reasons why I chose it. But you do need to have the book because we're going to refer to it constantly, and the homework problems will all come from the book, and the syllabus is described in terms of the book. So I'm going to be giving lectures Mondays and Wednesdays at 11 o'clock. The lectures will all be recorded, and within a half hour or so, the end of the lecture, the plan is that I will be able to post it on the YouTube channel. So if you miss a lecture, it's there. And if you want to see a lecture again, it's also there. Okay. There's a chat message, someone asking about audio. So you should be able to hear me. I certainly hope you can. If there's a problem, just let me know. Also, during the lectures, you should be muted, but whenever you have a question, do not hesitate, unmute yourself and ask me a question. So you can interrupt me at any time. So the syllabus and the lecture schedule and the homework schedule for the entire semester are already posted on Blackboard. And unless there are any questions about the administration of the course, grading and so forth, we will start to work right now. So, okay, so let's start. The first thing to say is that in linear algebra, we study vector spaces, vectors and vector spaces over a field. And let me explain for a second. So, okay. So check frequently. Also, when I need to communicate, I do it by email or by posting on Blackboard. I email via Blackboard. So that means that any emails I send out to the class go to the email address which Blackboard has for you, which typically is your Lehman College email. So that's what you need to check for communications from the class. Okay. So linear algebra studies, what did we study? Vector spaces. Is there a question?
I have a question.
Yeah, go ahead, please.
Is there any way you can make your screen bigger, like share your screen?
Well,
Like to
right
focus on.
now, This is basically filling up the whole screen.
Oh,
So,
okay, I see. I have to do it myself.
okay.
Thank you.
So linear algebra studies vector spaces and vectors, and also functions, sometimes called maps, between vector spaces. Right? And the vector space is something, I'll describe it formally in a few minutes, but it's described over a field. So the field you're most familiar with are the real numbers. And you often think of the real numbers as being on the real number line. So you have the real numbers, but you also have to know complex numbers. And a complex number is something which is a point in the ordinary XY plane that you're certainly familiar with from calculus and pre-calculus and high school algebra. So you might have a number A, which is a real number on the line. A complex number is just a point in the plane, AB. So your complex number, let's say, I'll call it AB. It's also sometimes written as A plus BI. So a complex number is just a point in the ordinary two-dimensional plane. And there are rules for addition and multiplication, subtraction, and division of real numbers. And there are completely similar rules for addition, subtraction, multiplication, and division of complex numbers. And we are going to work with vector spaces over the real numbers and the complex numbers. So if you're not familiar with the complex numbers, you really need to pay attention to the discussion in the book on the subject. It's in section 1A. It's literally the very first topic in the book, because you can't restrict yourself just to real numbers. We have to use complex numbers in mathematics. So how do we define addition of complex numbers? So we have a complex number, let's say alpha is A plus BI, and beta is C plus DI, where A, B, C, and D are real. So alpha plus beta, so that's A plus BI plus C plus DI. We take A plus C, those are two real numbers, and B plus D, those are real numbers, so we know how to add them. And this is the sum of the complex numbers. Right? So 7 plus 2i plus 8 minus 3i is 7 plus 8 is 15. 2 minus 3 is minus 1 is 15 minus I. Right? It's just an example. And the way we multiply complex numbers, alpha times beta, or A plus BI times C plus DI, this is defined to be AC minus BD plus AD plus BC times I. Right? That's the rule. Where does the rule come from? Well, if these were ordinary numbers and we could distribute across, this would be AC plus ADI plus BCI plus BDI squared. I squared is minus 1. So this is AC minus BD plus AD plus BCI. That's where the rule comes from. So for example, 7 plus 2i times 8 minus 3i, this is equal to 56 minus 6 plus 6. Right? Is there a question?
11. Yes. Yeah.
He's doing it online. Oh, it's online? No way, they're not.
I'm sorry. If there was a question, I did not hear it. So can you repeat it, please?
Sorry, that was not a question. Sorry.
Okay. So 56 plus 6 plus AD minus 21 plus 16i. So we get 62 minus 15i. That's multiplication. Or you look at another example, one which is in the text. 2 plus 3i times 4 plus 5i. That's 8 minus 15 is minus 7, and 12 plus 10 is 22i. So whether you're dealing with real numbers or complex numbers, they're basic properties of elementary arithmetic, which are always satisfied. So I'll call this properties of real and complex arithmetic. So the first is what's called commutativity. So for any numbers alpha and beta, alpha plus beta is the same as beta plus alpha, and alpha times beta is the same as beta times alpha. So you are certainly familiar with this with real numbers. And for complex numbers, let's just check. So if alpha is a plus bi and beta is c plus di, alpha plus beta is a plus bi plus c plus di. So you add the a and the c, you add the b and the d. But a, b, c, and d are real numbers. So a plus c is the same as c plus a. And b plus d is the same as d plus b. And this is exactly what you got if you took c plus di and added a plus bi to it. That is beta plus alpha. So this is a very elementary verification that alpha plus beta equals beta plus alpha. And what about for complex multiplication? What is alpha times beta? A plus bi times c plus di. This is AC minus BD plus AD plus BC times I. What is beta times alpha? That's C plus DI times A plus BI. That's CA minus DB plus CB plus DA times I. But C, A, B, and D, these are all real numbers. So CA is the same as AC and DB is the same as BD. And BC and CB are the same and DA and AD are the same. And addition of real numbers is commutative. So this is exactly the same as AD plus BC times I, which is alpha beta. So this is a very direct proof that addition and multiplication of complex numbers are both commutative. We also have for real numbers the associative rule. That is, we have what is called associativity. Right? So for real numbers, that says that A plus B plus C is A plus B plus C, and A, B times C is the same as A times BC. And you can check exactly the same thing is true for complex numbers. So for all alpha, beta, and gamma I'll write this sort of capital boldface C, this is the complex numbers. Alpha plus beta plus gamma is the same as alpha plus beta plus gamma. And alpha beta times gamma is the same as alpha times beta gamma. So just to check that you can do some elementary complex arithmetic, suppose alpha is 2 plus 3i, beta is 4 plus 5i, and gamma is 7 minus 2i. So compute separately alpha beta times gamma and alpha times beta gamma and check that they're equal. So spend a minute right now with a piece of paper and work it out.
For the beta, is that 9 or 4?
4 plus 5i.
All right. And gamma is 7?
Yes. How does it go? Let's see. So alpha beta 2 plus 3i times 4 plus 5i. I already calculated that. That was minus 7 plus 22i. So alpha beta times gamma is minus 7 plus 22i times gamma, which is 7 minus 2i.
Can see.
So let's see, what is that? That's minus 49 minus 44 plus 14 plus 7 times 22. 7 times 22 is 152i. So I get, if this is correct, minus 5 plus 166i. Oops, this should be a 154, I think. Makes this 168. Hope this is correct. Let's see about alpha times beta gamma. Beta gamma is 4 plus 5i times 7 minus 2i. So that's 28 plus 10 plus minus 8 plus 35. So that looks like 38 plus 28i. And so alpha times beta gamma, alpha is 2 plus 3i times 38 plus 28i. What is that? That's 2 times 38, that's 76, minus 3 times 28. 3 times 28 is 84. Oops, we already have a problem. Plus something times I, 3 times 38, that's 106, I think. And plus 56. So there's obviously a mistake somewhere. So I get 100 and minus 8 plus 162i. So good. I'm always happy when I make a mistake, check, or I'm happy when I do a problem, check and find the mistake. So then I can go back and try and do it right. So let's see. Let me go back to the original. 2 plus 3i times 4 plus 5i is minus 7 plus 22i. And if I multiply that by 7 minus 2i, I get minus 49 plus 44, which is minus 5. And the imaginary part is 14 plus 154, which is 168. So that looks okay. When I multiply beta and gamma, 4 plus 5i, 7 minus 2i, I get 28 plus 10, which is 38. And I get 35 minus 8. 35 minus 8 is 27. That's better. So this presumably should be a 27. So 2 plus 3i times 38 plus 27i, I get 76 minus 81. And I get 3 times 38 is 106 plus 54. So 76 minus 81 is minus 5. And 106 plus 54. Is that right? Still seem to have a problem. 3 times 38 is 116. I have to be able to do 3 times 38. No, it's not even right. 3 times 38, 3 8s are 24. 114 plus 54 is 168. And that's exactly what I did get before. Excellent. So the moral of the story is when you do a problem, check. And hopefully, what you did is correct the first time, but if you're not, the check will show you you made a mistake, and then you can go back and fix it. Okay. So this is just basically high school math with complex numbers. You probably didn't see complex numbers in high school. Maybe you did, but somewhere along the way, and maybe this is the first time, you have to learn about complex numbers and become familiar with their use. Actually, let's draw a picture of what happened when we took alpha equal to 2 plus, let's just do addition. Alpha equals 2 plus 3i, and beta equals 4 plus 5i. And when we add them, you add the real parts, 2 plus 4, and the complex parts or imaginary parts, 3 plus 5.
We can't see the paper. I think it's too
Yep.
far
there we go.
below it. All right.
So if you take 2 plus 3i and 4 plus 5i and you add them, you get 6 plus 8i. Let's sort of draw a picture. So the complex number 2 plus 3i is right here. This is the point 2 comma 3. That's alpha. 4 plus 5i I have to draw this well.
Can you go a little bit lower? Just a little bit more. All right. That's good. Thank you.
This is beta, which is 4, 5. And when you add them, we got the number 6 plus 8. Yeah. Let me take another pair of numbers because this picture is not very good. Let me try something slightly different. This is just a very geometrical, pictorial way to understand vector addition. So suppose I take the vector alpha equal to 3, 1. And I take the vector beta to be 2, 4. And if I take alpha plus beta, so this is the same as 3 plus I, this is the same as 2 plus 4i. Alpha plus beta is 5 plus 5i, which is like 5 comma 5. There's that, that's about there. And this is alpha plus beta, which is 5 comma 5. And if I were to draw a parallelogram with these two sides as the first two sides, this is really as if I took the vector alpha and the vector beta, translated the vector beta so the tip of beta was at the, that is the starting point of beta was at the ending point of alpha. I get this rectangle. If I were to draw this parallelogram, if this is alpha and this is beta, this is 0, 0, this is alpha plus beta. And from this picture, we sometimes say that complex addition, that's addition of complex numbers, is by the parallelogram rule. Of addition. That is, if you take two vectors, you make them the sides of a parallelogram, and the opposite vertex is the sum of the two vectors. So that's always a very nice geometrical way to understand addition of complex numbers. Now, in the real numbers, R, we have subtraction. That is, you can take 7 minus 4 and get 3. And what this really means is 7 plus the number -4, which gives you 3. And the basis of subtraction is the number 0. 0, the real number, has the property that for any number a plus 0 and 0 plus a are equal to a. And if you want to find the inverse under addition of a number a, you know that a plus the number minus a is 0. And that's why we can define for real numbers subtraction a minus b is sometimes or is the same as a plus -b. And we can do the same thing with complex numbers. So, of course, every real number a is a complex number also. Because a is a plus 0 times I. So in the complex plane, the point on the x-axis, a comma 0, this is a plus 0 times I, or a. Every real number is a complex number. 0 is a complex number. The real number 0 is also 0 plus 0 times I. That's just the origin. And how do you find the inverse of a complex number? If alpha is a plus bi, minus alpha has to have the property, that's another complex number, that alpha plus minus alpha is 0. So what do you add to alpha to get 0? Well, if you let minus alpha be minus a plus minus b times I, this is just another complex number. Alpha plus minus alpha, that's a plus bi plus minus a plus minus b times I. You add the real parts, a minus a, and you add the complex imaginary parts, b minus b. You get 0 plus 0 times I is 0. So for any complex number alpha, minus alpha is minus a minus bi. Now, there's one other property of ordinary real numbers I haven't discussed yet, and I can't leave it out, and that's division. Right? So in the complex number, in the real numbers, 1, the number 1, has the property that 1 times a and a times 1 equals a for all real numbers a. And if you have any number a, so long as it's different from 0, there is a number 1 over a such that a times 1 over a is 1, right? So for example, if a is 3/8, 1 over a is 8/3. And a times 1 over a, which is 3/8 times 8/3, is 1. So, and we can define division, b divided by a is just b times 1 over a. So what about for complex numbers? If alpha is a plus bi, not 0, how to construct or define 1 over alpha? That is, a number such that another complex numbers, say c plus di, such that alpha times 1 over alpha, or a plus bi times c plus di equals 1. Right? So that's an interesting question. Can we find the inverse of a complex number? So I could just write down the solution, but because I know what the answer is, but you should always be able to like solve a problem, even if you know the answer, or solve the problem if you didn't know the answer. So here is the problem. Given alpha equal a plus bi, find some number c plus di such that a plus bi times c plus di equals 1. And note, alpha, which is a plus bi different from 0, means either a is not 0 or b is not 0 or both, right? The only time a complex number a plus bi is 0 is when a and b are both 0. So at least one of these two numbers is not 0. I don't know. Let's see if we can solve this problem. If you take a plus bi times c plus di, this is equal to ac plus bd plus ac minus bd plus ad plus bc times I. And this is going to be equal to 0 plus 0 times I, if and only if, that's what this sort of double-headed arrow means, this is 0 and this is 0. AC minus BD equals 0, and AD plus BC equals 0. So that is, given A and B, find C and D. But this is a high school algebra problem. This is solving two linear equations in two unknowns. The unknowns are C and D. Let me write it slightly differently because the variables are C and D. This is the same as AC minus BD equals 0, and BC plus AD equals 0. How do we usually solve such equations? Well, this is just high school algebra. So you can take the first, let's say you want to eliminate D. So take the first equation and multiply it by A. Take the second equation and multiply it by B. Add the equations. A squared plus B squared. Oh, I'm sorry. AC minus BD, you want this to be equal to 1. So this should be a 1 over here. Equals 1. That's very important. Equals 1. So when I multiply this equation by A, I get A squared C minus ABD equals 1. So when I add these two equations, these cancel. I get a squared plus b squared c equals, oops, sorry, I'm multiplying this equation by a equals a equals a. So c is equal to a over a squared plus b squared. And then if I solve for d, d is minus bc over a. That's minus b over a over a squared plus b squared. The a's cancel. I get d is minus b over a squared plus b squared. So using this tiny bit of high school algebra, I solved the problem of doing division for complex numbers. So what I just proved is that if alpha is a plus bi different from 0, then 1 over alpha is equal to, what did I get? A over a squared plus b squared minus b over a squared plus b squared I. And notice, this is important. Alpha different from 0 means a squared plus b squared has to be positive. It can't be 0, because at least one of these two numbers is 0. So this is a positive denominator, and I can divide by it. And if alpha is a plus bi different from 0, and beta is c plus di, then beta over alpha is going to be c plus di over,
You can see the top part. Yeah, okay.
so if alpha is a plus bi, a non-zero complex number, what I just showed is that 1 over alpha is this complex number. This is the real part minus this. This is the imaginary part. So beta over alpha, which is c plus di over a plus bi, is c plus di times this, a over a squared plus b squared minus b over a squared plus b squared I, which I could write as c plus di. I could factor out, this is just a common denominator, everything over a squared plus b squared times a minus bi. So this explains how to divide complex numbers. So for example, if alpha is 3 plus 4i, then 1 over alpha is 3 over 3 squared plus 4 squared minus 4 over 3 squared plus 4 squared. So that's 3 over 25, this is I, minus 4 over 25i. And we can check. 3 plus 4i times 3 over 25 minus 4 over 25i is 9 over 25 plus 16 over 25 plus minus 12 over 25 plus 12 over 25i. These cancel. 9 plus 16 is 25 over 25 is 1. So, well, that's what it is. Anyway, complex numbers are fun, and they are definitely very important. And there'll be some homework problems involving complex numbers, which I will assign. Homework will typically be due every Monday. So these are just numbers. What about vectors and vector spaces? So the basic, most fundamental vector space comes from making a list of fixed length of numbers. So real numbers and complex numbers in linear algebra, there's just another name for these things, are called scalars. So a scalar in linear algebra is either a real number or a complex numbers. And R and C are examples of what in algebra is called a field. I mean, for us, the only fields we're going to consider are the reals and the complex numbers. And sometimes, often in fact, we use F for field to denote either R or C. So if there's some proposition which is true for the reals and true for the complex numbers, also, we don't want to have to write it down twice. We say it's true for every field F. So another name for one of these numbers is a scalar. So the scalars are the real or complex numbers. These are examples of fields, and we just use the letter F as a generic symbol for either one of these two fields. Okay. So what are some examples of what will be our basic vector spaces? So let's just write down a few concretely. R2, this is the set of all pairs, let's say X, Y, where X and Y are in, this means in the real numbers. This is our picture of R2, it's just the ordinary plane. A point is X comma Y. Sometimes we write this as X1, X2. It's just an alternate notation. R3 would consist of all triples of numbers, X, Y, Z. Which we would also write sometimes as X1, X2, X3. And, you know, sometimes you picture this in three-dimensional space. This is the X, Y, and Z axis. And of course, there's no reason to stop at 2 and 3. You can look at R4. This would be a list, all lists of 4 numbers, all of them in R, or R17. You would have lists of 17 numbers, where this list has 17 entries and the order matters. If you take the list 2, 3, that's not the same as the list 3, 2, right? The order matters here. So this set, this will turn out to be one of our basic vector spaces. That is all lists of a finite length. And if whatever we do for the reals, we can usually do as well for the complex numbers. So C2 would be the set of all complex numbers Z1, Z2. We would call this something like two-dimensional complex space. Or C3 is all lists of 3 complex numbers. And C4 would be lists of 4 complex numbers and so forth, right? These are core examples of a vector space. And so just to be able to condense this notation, what we call Fn is all lists of n numbers, x1 up to xn. N is fixed. You fix the n and then you only look at lengths of exactly n elements, where all of these elements, x1 up to xn, belong to the field F, whether it's the real or the complex numbers. So this is all very standard notation. And an element, the elements of this set, these are called vectors. These are all examples of vectors. This is just one case. And there are 2 operations on vectors. We have what is called vector addition. In this set Fn. And it's defined as follows. If you take x1, x2 up to xn, that's one element. And y1, y2 up to yn, that's another element. You add the numbers in the corresponding places in the list, what are called the coordinates. x1 plus y1, x2 plus y2, xn plus yn. So for example, 2, 7 plus 3 minus 9 is 2 plus 3, comma, 7 minus 9. That's the vector 5 minus 2. Or the vector 1, 2, 3, 4 plus 5, 6, 7, 8. This is in F4. This was in F2. You add 1 plus 5, you get 6. 2 plus 6 is 8. 3 plus 7 is 10. 4 plus 8 is 12. That's vector addition. If these were complex vectors, 3 plus 2i minus 7, 8 plus I. So this is in C3, right? This is a real number, but every real number is a complex number. Plus minus 2 plus 5i, 1 plus I, 9i. When you add the first components, 3 plus 2i plus minus 2 plus 5i, minus second components, minus 7 plus 1 plus I. Third components, a plus I plus 9i. So here we get 1 plus 7i is the first coordinate, minus 6 plus I is the second, and 8 plus 10i is the third. That's the sum in C3. Okay. All right. Any questions about this so far? So we have this operation of adding vectors. This is vector addition. But there's also an operation of scalar multiplication. So here we take a vector and there's a rule to multiply it by a scalar. That means to multiply it by a number. And the rule is the following. Suppose we take a scalar lambda in the field and a vector x1 up to xn in Fn. We define lambda, the scalar, times the vector as the vector you get by multiplying each coordinate by lambda. So that's lambda x1, lambda x2 would be the second coordinate up to lambda xn. So for example, if we took 7 times the vector 3, 2, minus 1, you multiply each coordinate of the vector by 7. You get 21, 14, minus 7. Or if you take, let's say in the complex numbers, lambda to be equal to 1 plus I. So lambda times the scalar, I don't know, times the vector 2 plus I, 3 minus 4i. So I'm multiplying 1 plus I, that's scalar, times the vector 2 plus I, 3 minus 4i. So that's, you multiply each coordinate by 1 plus I. I get 1 plus I times 2 plus I, and 1 plus I times 3 minus 4i. And I'll work it out, but let me give you a minute to work it out yourself, just to get a tiny bit more practice with complex numbers. So what is the vector that you get in C2? Right, we're in the complex numbers. Let's see. Can anyone tell me the answer? What is 1 plus I times 2 plus I? When I multiply these two complex numbers, what do I get? So the real component will be 2 minus 1 is 1. And the imaginary part, I get I plus 2i is 1 plus 3i. That's the first coordinate. And for the second coordinate, I get 3 plus 4 is 7, and 3i minus 4i minus I. So this, if I take this vector in C2 and multiply it by this complex number, this is the vector that I get.
Excuse me, Professor.
Yeah.
The thing is, like sometimes, I don't know how that happened, probably someone else, it's like we cannot see clear the numbers. The number, like, are close to the eye sometimes. Sometimes I think like the 4 is the 9, and then sometimes, like, that's the situation that I don't answer immediately to you, just to let you know.
Yeah, okay, well, but again, if I write something down and it's not clear, just ask me, right?
Okay,
You can
thank you.
interrupt at any time to ask a question.
And I had another question.
Go ahead.
Everything like you are writing now, we can see it later on YouTube, right?
Correct.
Yeah, thank you.
Yeah. Once in a while, I forget to record the lecture, which is terrible. But normally, every lecture is recorded, and I post it as soon as the class is over. it takes 15 or 20 minutes usually to get it up on YouTube.
Thank you.
So
That
you
will
can
help
see
a
it
lot.
there at any time. Of course, if you can't read my numbers on the screen, though, that won't look any different on YouTube. But so again, if you have a question, always just interrupt and ask.
The thing is, can I continue talking?
Of course, go ahead.
The thing is, for me, for example, it's more important to pay attention what you are doing than, to be writing. That's
Yeah,
why.
I agree. And that's completely up to each student, how much to take notes, how much to just pay attention. But in any case, the video will be on YouTube, so you can always watch it there. But
Thank you. Thank you.
everything else is, you are free to choose what to do. Okay, so these spaces like R2 and C2 and so forth, these are examples of vector spaces. There are many more vector spaces than these, though these are the most important ones, especially in the beginning of the study of linear algebra. So what I just discussed was section 1A, that is chapter 1, section A. And in 1B, there is the general definition of vector space. And whenever you define a vector space that's denoted by V, it's always over, you have to say what is the field, real or complex numbers you're working over, but over some field F, which for us is always either the reals or the complex numbers. And the definition is the following. A vector space is a set V, not empty. So there really is something in the set with two operations of vector addition and scalar multiplication. So what vector addition means is for all vectors, an element of a vector space is called a vector. For all vectors V1, or let's say for all vectors U and V in the vector space V, there is defined a vector U plus V. That is, there's some operation that lets us add vectors. And for all vectors V in the vector space and all scalars lambda in the field, there is defined a vector lambda times V in the vector space. Again, this funny symbol means in, lambda V in the vector space V. So we already saw the basic example of that when you have a field F and the vector space is just the list or n tuples of elements of the field. You add coordinate wise and you multiply coordinate wise. Those are the basic examples. And vector addition and scalar multiplication have to satisfy the standard properties, the usual properties we like. Namely, addition is commutative and associative. There is a vector, not a number. There's a vector 0 in the vector space such that 0 plus V and V plus 0 are equal to V for all vectors in the vector space. And if you take the number lambda equal to 1, 1 times any vector is the vector for all v in the vector space. So there's always a zero vector. You can add, which has this property, you add the vector 0 to any vector v, you just get back v. And the number 1 has the property, the field always contains the number 1. 1 times any vector is just the vector. All right. Just to make this very concrete, in Fn, the 0 vector is just the vector with all coordinates equal to 0. Because if you take v to be the vector x1, x2, x3 up to xn in Fn, the vector 0 plus the vector v when you add coordinates, you get 0 plus x1, 0 plus x2, up to 0 plus xn, which of course is just x1 up to xn, which is v. So 0 plus v equals v. This is the 0 vector in Fn. So all of the nice properties of vector spaces that are obvious in Rn or Cn or Fn, we can prove are true in general. Let's see, what are some of these things? So we have a distributive law. So for all scalars, lambda in the field, and all vectors u and v in the vector space, if we take lambda times u plus v, that's lambda u plus lambda v. And there's another distributive law. For all scalars, lambda and lambda prime in the field, lambda plus lambda prime times any vector is lambda times the vector plus lambda prime times the vector. So I claim if you take any vector v and multiply it by the number 0, maybe just to emphasize this, I'll put 0 with a little like arrow kind of thing over it as like, that means the 0 vector. So I claim if I take 0 times any vector, I always get the 0 vector. Okay. So this is the sort of thing you think should be true, and maybe it's sort of obvious, but it's a claim. So I must prove this. Why is it true that if you multiply a vector by the number 0, you get the 0 vector?
Can I say it?
Why?
Yes, because if you multiply 0 for any coordinate, that would be 0.
Ah, that's correct. So let's say that obviously true for the
Bless you.
vector space equal to Fn, because 0 times x1 up to xn, you multiply each coordinate by 0, you just get 0, right? So what you said is 100% correct for Fn. Okay,
Can I say something?
go ahead.
Okay, that means it does apply like 0 times v is the vector 0. That means if I multiply by 1, that would be like would be the B vector. But I believe you will continue with that. I'm just trying to follow. Probably that rule apply, the other one apply too.
Right, that is also correct. However, so everything you said is correct, but it's not enough because Fn is not the only vector space. There are other vector spaces. Let me give an example. In calculus, let V be the set of all continuous functions F on the real line, okay? I claim V is a vector space. Why? Because the sum of continuous functions is a continuous function. The product of continuous functions is a continuous function. So this set of all continuous functions, like what are some examples? F of x equals x squared, f of x equals sine x, f of x equals e to the x. These are all continuous functions, and this is a vector space, right? It's that because you can add continuous functions and you can multiply continuous functions by scalars, and all the properties of continuous functions are satisfied. So this is an example of a vector space. So the argument that was just given, that if you multiply a vector in Rn or Fn by a scale by 0, you get 0, that's correct. But what about in this case? It's a little bit different, right? So there are many vector spaces. So the moral of the story is many vector spaces exist, not only the Fn vector spaces. Okay. So this is maybe the point I'm about to make is maybe a more refined point for people who might go on to study mathematics or major in mathematics, but let's give a proof. Let's prove 0 times V is the 0 vector for all vectors in the vector space. And we use the fact that 0 plus 0 is 0. Okay? Everybody agree to this? Anyone object?
Nope.
Good. So 0 times the vector is the same as 0 plus 0 times the vector, because 0 equals 0 plus 0. Right? So right here, I'm using this. And of course, this is the same as 0 times V plus 0 times V, because we have a distributive law, lambda plus lambda prime. Any scalars is lambda V plus lambda prime V. Right? This is a distributive law. Right? And so 0 times V is a vector space, so it has an additive inverse. So there exists something, let me just call it U, such that U plus 0 times V is the 0 vector, right? Right? For any vector V, there's always a vector minus V, which gives you 0. That's one of the axioms of a vector space. So this U is like minus 0 times V. So I have this equation, 0 times V is 0 times V plus 0 times V. Let me add the negative to this. So 0 times V plus minus 0 times V is the same as 0V plus 0V plus minus 0 times V. I'm just adding this to both sides of this equation. But of course, here, if I take a vector and it's negative, I get 0. And over here, I have the associative law. This is the same as 0 times V plus 0 times V plus minus 0 times V. And this is the 0 vector. And the 0 vector added to anything doesn't change the anything. This is 0 times V.
We can't see.
So if you look at this strange equation, it says the 0 vector is 0 times the vector V. And that was what I needed to prove. So again, this is maybe a little bit more sophisticated than much of what I'm going to require in the class, but it's just interesting to see how one proves things in mathematics. So if you have the ordinary, the most familiar vector spaces, Rn and Cn or Fn, the statement is obvious from just the definition of scalar multiplication. But there are many other objects in the universe that satisfies the conditions for being a vector space, like those continuous functions. And this is a proof that no matter what vector space you're in, if you multiply by 0, you always get the 0 vector. Okay. So what I've just covered is exactly what on the lecture schedule I said I wanted to cover today, which is sections 1.A and 1.B in chapter 1. So you really should, if you can, review this before Wednesday's lecture, and maybe read ahead to section 1.C, which is what I'm going to talk about on Wednesday. All right. Let's see. I see there's some things in the chat, but nothing I seem to need to reply to. Okay. Any questions before we end for the morning? Actually,
Okay,
Yeah.
I have a question.
go ahead.
I was looking at the book, the one, that you recommended, Sheldon Axler. And I think, everything is there. I believe, like you say, we read in advance the section 1C. I believe we will have no problem because it's following what you are telling us right now.
Correct. That's true.
Okay, that's important because that will help us a lot. But thank you.
Yeah. I mean, it's always good to know what's in a lecture before you hear the lecture. So if you can read ahead, that's really very good for you. I mean, for
Yes.
learning.
I will follow that.
We
Okay.
have,
Any more questions?
About, I'm sorry because I just came in a little late. I don't know, probably you explained at the beginning. Did you explain about the exam 1 and 2 of how you would do it? How we will work on those assignments that you say, like you usually on Monday it's homework.
Correct.
All right, today we don't have homework, thank God, right?
Oh, no, not today. Today we just started.
Okay, thank you. Then that means that we have to be prepared for next Monday and Wednesday, right?
Correct. So I will post an email to everybody, the homework assignment for next Monday.
And sorry because I'm talking too much because I'm new on Blackboard. Do you think like it's not complicated for me later on to submit or work on those assignments from you?
So as I said and explained them, so if you've never used Blackboard before, it's complicated. So most people, you know, if you've been at Lehman, you know, for previous semesters, you've used Blackboard because everybody, I think everyone who's teaching uses Blackboard. Almost everyone does, I think. In any case, the way you do your homework, as I said, and also the exams, you write out the solutions to the problems. Then you have to convert your pages to a PDF file. So most printers have a feature that you can scan a document and make it into a PDF file. And then you upload the PDF file to the assignment section on Blackboard. The only way I can see your work and graded is if it's uploaded to Blackboard. All your grades will be on Blackboard. Everything, all the grading is done on the computer. But you do need to get to Blackboard and figure out, make sure you can open up the website for this course and read everything that's on there. There's a lecture schedule, there's information about the syllabus, the textbook, the link to the YouTube channel where all the videos of the lectures are posted and so forth. All the information I give is on Blackboard. And when I have to communicate to students, it's always via the email function on Blackboard, which sends an email to your Lehman College email account. So you need to be able to get that, read those emails.
Good. I don't know if someone else had a question because I had a lot of questions, but I had another one. Sorry about it.
Go ahead.
Okay, I'm coming from CLIP, the program from BCC,
Okay.
and then they show me how to use
Wait, you didn't
Junior.
use Blackboard at BCC?
They didn't because we were not like in college because that's a program to prepare us to to come to college. And then because we don't have register, we were not registered in college. We were not allowed to work on Blackboard. And in the last hour, I remember they told us introduction. But that was an introduction for less than an hour, and that's it. But I will do my best to be, to work on Blackboard because I need it and had to do your job, your assignment.
Right.
But I have another question. I learned how to use Junior Scan because any picture we take is like a PDF. Can I use that to submit it to you?
Sorry, to use, what did you use?
Genius, they call Genius Scan. It's a program that
It's an app on the phone.
Yeah, there is an app on the phone that we use, and then it's very easy for me because that's why I was submitting those PDF in my class.
So when you use your phone, you have to take an individual picture of each page?
Yes, that's the way that we have to use it, but they send it all together as one, the program. And then I can choose, where to send it by email, and then probably I can work on
you
Blackboard.
can't send it by email. You have to
upload it, right?
You have to upload it to Blackboard.
Okay,
And
I will find a way.
if you can do that with the homework assignment and upload it, fine. But you'll know in a week because when you'll see whether or not you're successful at uploading your homework.
Good. Okay. I will try, and then I see. I just wanted to know if I had the option to try.
Yeah.
You can
So
use it.
the other
I
thing
use it
is you can
second.
always, there should be at the computer help desk at Lehman, people who can help you with Blackboard and with uploading assignments to Blackboard.
And my last question to you.
Go ahead.
Okay, I'm coming after 31 years, you know, because I got my bachelor degree in Santo Domingo
Okay,
31 years ago. What do
okay.
you recommend to me?
I have
to
no
study?
recommendation. I mean, what is there to recommend? You have to study and learn.
Yeah, I got it.
That's
But
all.
any
I mean-
any special thing, because you know, 31 years after to try to come back, it's a little
Well,
hard, but
How
that's
much
my problem.
mathematics did you study in Santo Domingo?
I just I got my bachelor degree in mechanical engineering.
So you had a lot of math and calculus,
Yes, I did.
differential equations?
Yes,
Yeah. So,
but let's see. I had to review everything.
well, it's not so much that you have to know any of the material. It's from that you learned when you were studying mechanical engineering. It's more that you have, you can reacquire or, you know, polish your math skills. It's, you know, it's like being able to think mathematically and solve mathematical problems. You don't need to know calculus for this course. The reason why calculus is a prerequisite is for most students, when you take calculus, you're learning how to think about mathematics and solve mathematical problems. So it's like the general mathematical reasoning skills that you develop in calculus that you need here. And it's more the ability to reason in mathematics and actually do calculations correctly that you need to do. It's, you know, it's like an athlete who has to warm up, you know, like, you know, you have to train, and part of the training isn't so much specific to your sport, it's fitness and endurance and, you know, whatever, all that. So that's really what you need. It's like the sort of mathematics training you have to, if you haven't done any mathematics for a long time, then you really have to work hard to get back into the mathematical way of thinking.
Yeah, thank you.
Yep. Anything else? Anything?
I just-
Okay, everyone, stay warm. I will be back on Wednesday at 11 o'clock.
Thank you, Professor. Have a great day.
Thank you. You too. Bye-bye.
Bye.
Have a great day.